بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. Can you hear me شباب؟
عليكم السلام. Yes.
الله يعطيكم العافية. طيب, بسم الله الرحمن الرحيم. Today's lecture will be the 28th lecture, and today's lecture will be the last lecture that we cover something new. So inshallah, starting from maybe tomorrow, if we have time, we're going to review we're going to solve some exercises on chapter 7, 8, and 9. For that reason, so please pay attention here. And before we start, let me go through a few announcements. So the first one is homework 4 is inshallah due this Sunday at 11:59 p.m. Quiz 5 will be inshallah tomorrow, and the coverage will be chapter 8, basically 8.1 to 8.4. Right. If you recall from last time, what we did was the following. So we started with so let me just give you a quick review here. Okay. So here, let me just go over what we did last time. So if you recall, we defined or we introduced the notion of phasors, and we said like if we have a sinusoidal source, then the output or the response of the circuit, when we say like the response, meaning that the current or the voltage at any point in the circuit is going to be a sinusoidal source. Let me use cosine here. A cosine omega t plus plus phi. If it's an input to a circuit here with capacitor, inductor, and resistor, meaning a linear circuit, then the output, meaning that the voltage, the voltage or the current at any part of the circuit will be of the same nature. It's going to be sinusoidal, but with different amplitude and different phase. So the thing is, like, instead of writing everything in time domain, where we have things that are fixed and things that are changing, so let's actually write it in a more compact way, or in a way to capture things that are changing. And it turns out if you use the notion of phasor transform, then this input will be written like this. So only this representation is capturing the amplitude and the phase. Again, this one is complex, meaning that this one is can be written as a cosine phi plus j plus aj sine phi. So we said, like, instead of writing instead of using real numbers, so we can use complex number, but it might look in the first glance as if it's complicated, as if we were complicating the way of solving this problem, but in fact we are simplifying it. And we saw last time how this simplification was achieved when we applied or when we tried to solve problems on finding Thevenin and Norton equivalent circuit, as well as source transformation. Okay, we said that, well, this is going to be the first step. So we're going to take our sources the voltage and the current sources and turn them into phasor. There is a missing step here that we need actually to write the frequency domain representation of our circuit element. Meaning that if we have a resistor, then the impedance of the resistor is going to be the resistance itself. If we have an inductor, the impedance of the inductor is going to be j omega L. If we have a capacitor, the impedance of the capacitor is going to be j omega C. I'm sorry, it's going to be negative j divided by omega C. Okay, that's what we did last time. And near the end of the class last time, Yasser asked the question is, what happens if I have sources with more than one frequency? Then in this case, you need to apply phasor transform. You need to apply superposition and phasor transform for each single frequency. Okay, any questions before start? Okay. This is a problem that we carried out from last time. So in this problem, we're asked to find the Thevenin equivalent circuit with respect to the terminals A and B. Again, we're asked to find V Thevenin between A and B, and R Thevenin between A and B, or Z Thevenin between A and B. So now we're talking about impedance. So what we can do here is we can actually apply node voltage method, even though we did not cover node voltage method yet when it comes to solving problems, but we can apply node voltage methods here. So if this is the reference point, this one is V1. Again, this one is in the phasor domain. We know the voltage here. It's going to be 10 multiplied by Ix. And V Thevenin is related to this voltage by voltage division. So V Thevenin is going to be minus J10. 10 minus J10 multiplied by 10 Ix. Ix is also V1 divided by 20. Yes, Abdullah.
I want to participate.
Oh, okay. Okay, so let's write the since you raised your hand, so let's write the node voltage equation for V1. So what is the node voltage equation for V1?
Since the current enter the node, we will have with the angle with the negative sign.
Okay, so starting from this one, it's going to be negative 2, 45 degrees. Okay. Then we have V1 divided by V.
Yeah, over 20 plus V1 minus 10 Ix over J10.
Yes, exactly. Plus V1 minus 10 Ix divided by J10 equals to 0. Okay, very good. So when we cover this part, when we have a resistive circuit, we usually keep it as it is. We tend not to simplify it, but here it's really better to simplify things, and this simplification is will be very useful. So most of the calculators do not allow you to invert a matrix invert a complex matrix. So you have to be careful here. Anyhow, so it's going to be V1 divided by 20 minus 245 degrees plus V1 divided by J10 plus, we know that Ix is V1 divided by 20, so 10Ix, meaning that it's going to be 10 divided by G20 it should be minus. Okay, hold on a second. I think I'm in a mistake. Okay, minus 2, 4, 5, 8. Okay. Okay, this one should be plus. This one should be minus. Yes, plus and minus. And Ix is going to be V1 divided by 20. Okay, Ali, question?
No, doctor.
Okay. So you can solve for V1. I'm not going to spend time on solving for V1. This is going to be straightforward. So all what you need to do is you have one equation, so you don't need to invert any matrix. Once you find V1, you can find Ix, because you know Ix is V1 divided by 20. And once you find Ix, you will find the Thevenin voltage. And if you do that, V Thevenin will be 10 and the angle is 45. Hadi?
Doctor, why is it 10 over J20, not J10? In the first equation.
Oh, okay. 10 over J10. Okay. Here, this one is. You mean this one?
Yes.
Okay. Should be fixed then. 10 over J10. Yes. Okay. Okay. Hadi?
Yes. Thank you.
Okay. So if you solve for it, you will end up with this equation. So I'm not going to spend time on manipulating complex numbers. Now, let's see what happens when we need to find, if I ask you to find the Thevenin equivalent impedance here. So since we have a dependent source, we cannot just simply deactivate all sources. So if you have independent sources, then you can deactivate all sources and you will find the Thevenin impedance. It's going to be straightforward. But here we have two possible methods. The first one is to find the Norton current, or the short circuit current between A and B. And the second one is to apply a test source. So let's apply a test source. So remember, if you are applying a test source, you need to deactivate all independent sources, and we have one, which is the current source. So if we deactivate it, it's going to look like an open circuit. Okay, so it's an open circuit. So this is 20. J10. Ix. Then ohm. And since we are applying a test source here, And this is Ix. Okay. So let's note something here. So we know that 10Ix by KVL is going to be 20 plus J10Ix. صح شباب؟ Following? We apply KVL in this loop. You will see that 20 plus J10 multiplied by Ix equals to 10Ix. صح?
صح.
Okay.
صح.
Okay, so what does it imply here? It implies that Ix equals to 0. Why? Think about it this way. You have Ax multiplied by equals to Bx. Then if A is not equal to B, then X must be 0. So this implies that Ix is 0. So if Ix is 0, what does the independent, what does the dependent source look like?
0.
Yes, exactly. It's going to look like a short circuit. So this implies that if we draw the circuit, it's going to be 20 J10, and this is the location of the dependent source. Okay, so now we know that we have a J10 plus 20 in parallel with a short circuit. So this implies that the parallel combination is 0. And we can see that Z Thevenin equals to V Thevenin divided, or V test divided by I test. I test is by KCL is going to be the current here plus the current here. So it's going to be V test divided by 10 minus V test divided by J10. So in this case, Z Thevenin is going to be 5 minus J5 ohm. So the Thevenin equivalent circuit is going to be, I think, 1045. Since we have a negative imaginary part, so it's going to be capacitor. Any questions? Okay, very good. So now let's move to node voltage method. Although we solved one problem somehow related to node voltage method, but let's solve a node voltage method question, and then we'll move to mesh current method. So we're not introducing any new concept. The only new concept here, or the only thing new here, is that we're going to deal with complex numbers instead of real numbers, and this might raise some issues here if you don't know how to deal with complex numbers. So let's apply the node voltage method. Who wants to help me applying the non-faulted method. Remember, our ultimate goal is to find IA, IX, and IC and IB. And let's start with Abdullah al-Mshiri. So let's, Abdullah, label the. Let's first label the nodes that we need.
So the top left will put it as V1.
Okay.
And the top right will make it V2 between the 2J and 5 resistor.
Okay. So we have V1, V2, and J. Okay, excellent. So what is the okay? So what is the first node equation? Let's see. Let me get some. The Kareem.
It's gonna be V1 over 10, and plus V1 minus V2 over 1 plus J2 plus 10.6 angle 0.
It's minus 10, not plus.
Minus.
Okay, good. So let me simplify it. So if I simplify it, I will try to make sure that I don't have complex numbers in the denominator. So I'll multiply both sides by 1 plus J2. So if you multiply both sides by 1 plus J2, you will get you'll get 1.1 plus J.2 V1 minus V2 equals to 10.6 1 plus J2. Okay, the reason we have 1.1 is that we have 1 from here, 0.1 from here, and that's why we have 1.1. So I combined 2 steps here. Okay, this is the first equation. The second equation, Ibrahim.
It will be V2 minus 20 IX over 5.
Okay, V2 minus 20. This is V2. Okay. So it will be V2 minus V1. V2 minus V1 divided by 1 plus J2.
J2.
Then we have what?
V2 minus 20 IX over 5.
V2 minus 20 IX over 5, exactly.
Then we have minus V2 over the capacitor.
Yes, which is J5. Okay, so if I move one of the, if I manipulate it here, it will be something like this. So I don't like to have a complex number in the denominator. So this J, I'm gonna move it to the numerator. So I'm gonna take the negative sign of it. So it's going to be something like this. Then V2 minus 20 IX divided by 5 equals to 0. So what is IX, Al-Hamidani?
Ix will be V1 minus V2 over 1 plus J2.
Exactly. So Ix is going to be V1 minus V2 divided by 1 plus J2. Okay, so I need to substitute because in most of the calculators, it will be much easier to solve it if we have two equations and two unknowns. So let me substitute. So I'm going to get V2 minus V1, 1 plus J2 plus J V2 divided by 5 plus V2 divided by 5 minus 20 divided by 5, which is 4. Ix is V1 minus V2, 1 plus J2 equals 0. So is this clear, Shabab? Any question? Okay, very good. Okay, let me now multiply both sides by 1 plus J2. So I need to get rid of the complex number in the denominator. So I'm going to get V2 minus V1 plus J divided by 5, 1 plus J2, V2 plus 1 over 5, 1 plus J2, minus 4 V1 minus 4 V2 equals to 0. So if I group the V1 terms, it's going to be minus 1 minus 4 V1. The V2 terms, they're going to be 1 plus J divided by 5 minus 2 over 5 plus 1 over 5 plus J 2 over 5 plus 4 equals to 0. So if I simplify it, again, your calculator will add these complex numbers. V1 plus 4.8 Okay. Ali, question?
Doctor, in the previous question, it is plus 4v2. You put it minus.
Oh, here?
Yes.
Okay, thank you. Okay. So now I have two equations, two unknown, V1 and V2. So let me write it in a matrix 4. So if I write it in a matrix 4, let me write it this way. Okay, it turns out there is a way of solving this problem using something known as Cramer's law. So it turns out that X is D divided by, or D1 divided by D. Y is D2 divided by D. So what is D, what is D1, and what is D2? So D is actually the determinant of this matrix. A1, B1, A2, B2, and we know that the determinant of this one is A1 B2 minus A2 B1. D1 is actually the determinant of this matrix, the same matrix here, but the first row, the first column is replaced by the solution, C1 and C2. So we'll take this one. I'm going to replace the first row, the first column by C1 and C2. So C1, C2, B1, B2. And the determinant of this one is going to be C1, B2 minus B1, C2. D2 is going to be exactly the same, but now I'm going to replace the second column with the solution. So now, if I find D1 and D2, I can find X and Y by taking the ratio. Is it clear, Shabab? Why am I doing this?
So you can find it separately, Doctor.
What's that?
And maybe can you repeat the question, Doctor?
So why am I doing this? Why am I using Kramer's law?
To simplify our calculation.
Exactly. So I'm trying to simplify the calculations. But why did not I use it when trying to solve back in chapter 4? Why I used it here? Why not in chapter 4? Ziad?
Because there is an imaginary part.
Okay, exactly. So most of the calculators cannot handle inverting matrix with the imaginary parts. So we're trying to find a simple way of solving this. But all calculators actually can handle the multiplication and addition and of complex numbers. Okay. So let's see what we have in here. So the matrix we have is going to be equation 1 is 1 plus 1 j plus 2 minus 1. Equation 2 is minus 5, 4.8 plus j6. J.6. The solution for the second one is 0. For the first one is 10.6 plus 10.6 multiplied by J2. Okay, so this term is A1, B1, A2, B2, C1, C2. So B is going to be A1 B2 minus A2 B1, and if we solve for it, we'll end up with 0.16 plus J 1.62. I'm sorry, this is D. D1 actually is very simple because here C2 is 0. So that implies that this implies that we have only one term here. So it's going to be C1 multiplied by V2. And if we do that, it's going to be 38.16 plus D2 is going to be, again, since C2 is 0, so it's going to be minus A2C. And if we do that, we'll end up with 53 plus J1. Okay. V1 will be D1 divided by D, and if we do that, we'll end up with 68.4 minus J, 16.8 volts. V2 will be D2 divided by D, and if we solve for it, we'll end up with 68 minus J, 26 volts. Okay, so now I found a V1 and V2. Remember, I was asked to find IA, IX, IC, IB. So I know that IA is going to be V1 divided by 10. IC is V2 divided by negative J5. IX is going to be V1 minus V2 divided by 1 plus J2. And IB is going to be V2 minus 20IX divided by 5. So I'm not going to find their values. So if you want to find their exact numerical values, you will need to refer to the textbook. Okay, any questions about Mohammed?
Yes, doctor. How can we solve the matrix if we have a 3 by 3?
Well, you try to avoid having 3 by 3 by either well, if you have 3 by 3, then in this case you can actually apply Kramer's rule, but you need to find the determinant of 3 by 3 matrix instead of 2 by 2 matrix. This is one option. The other option is you try to eliminate one equation, and you will end up with 2 by 2 equation, a 2 by 2 matrix. Any other question? Okay. Okay, now let's try to apply a mesh current method and try to solve for, try to find V1, V2, and V3. So clearly V1 is the mesh current in the first part multiplied by 1 plus J2. V3 is the second mesh current multiplied by 1 plus J3. And I'm sorry, V3, and V2 is going to be IX multiplied by 12 minus J16, and IX is going to be related to the mesh currents. So let's try to find the mesh currents here. Ali, question?
No, I want to participate.
Yeah, go ahead.
For mesh A, it will be minus 150.
Okay, so let's label them.
Plus 1.
Okay. So it's going to be 150 Okay, I just
plus
move.
1 plus J2 IA plus 12 minus J16 multiplied by I1 minus IA minus I2. Or IB, yes.
Okay, very good. So if I simplify it, well, actually it's already simplified. But if I simplify it, I will end up with 13 minus J14 IA minus 12 minus J16 IB equals to 150. So this is the first equation. The second equation, so let's see al-Mashtari.
Yes, doctor.
Yes, go ahead.
12 minus J16 times IB minus IA.
Okay. So let's write it. 12 minus J16 IB minus IA. Okay.
1 plus 3J times IB. Plus 39 IX.
Plus 39 IX. So back to Muhammad's question. Well, in this case, we need to find an equation for IX, or we can find an expression for IX and substitute it into this equation. So what is IX? So let's see, Yasser.
Yes, IX is IA minus IB.
IX is IA minus IB, exactly. Okay, so now IX is IA minus IB by applying KCL here. So let's simplify this equation. So if we simplify it, substitute IX, we will get 27 plus 6 IA minus 26 plus J13 IB equals to 0, and this is the second equation. So I have two equations, two unknowns. I can, we know that A1, let me write it in matrix form. 13 minus J14 minus 12 27 plus J16 minus 26 plus J13 IA IB, and this one was 150. This one is 0. Okay, so D is going to be the determinant of this matrix. So it's going to be A1 B1 minus A2 and it's going to be 60 minus J45 D1 is we replace the first column with the solution. Since we have 0, so all what we care about is C1 multiplied by B2. And in this case, we're getting minus 3900 minus J 1950. D2 is going to be A2 multiplied by negative A2 multiplied by C1. And if we do that, we'll get minus 450, 4050. Minus J 2400. Please double check the signs here. Make sure that, because I think I made a mistake in my handout here. So please check this. Okay, so I1 is going to be D1 divided by D2, D1 divided by D, and this is going to give you negative 26, negative 52 amperes. I2 is going to be D2 divided by D, and this is going to give you negative 24, negative J58 amperes. IX, this is IA, this is IB, and it's going to be minus 2 plus J 6 amperes. So once you find them, once you find IA, IB, and IC and IX, you can find V1. So V1 is going to be IA multiplied by 1 plus J2. V2 is going to be IX multiplied by 12 minus J16. V3 is going to be IB multiplied by 1 plus J3. So the exact numbers are in your textbook. So any questions, Shalom? Okay, so the last problem that I want to solve is this problem, and the difference between this problem and the previous ones is that in this problem we need to do one step further here. So previously the circuit element that were given, their impedance were given to us. But in this circuit, we have to find the impedance of every single element. We have to convert sources into phasors. So let's start with the sources. So let's convert them into phasors. So VA is going to be the phasor form of VA is going to be 18. The angle is negative 90. The phasor form of this one is minus J80. The phasor form of VB is going to be 12 or simply 12. So now let's convert this into phasor. So it's going into impedance. So it's going to be negative J divided by omega C. Omega here is 4000. C is 625 nanofarad. So if you do the math, you will end up with negative 400, negative J400. For this one is going to be J omega L, and L is 25 millihenry. Omega is 4,000, so you will end up with J100. And for the resistors, their impedance is exactly the same as the resistance. So let's apply the mesh current method, IA, IB here, to find V naught, which is the voltage across the 25 millihenry inductor. Okay, so let's apply the mesh current method here. Let's start with the first loop, with the first mesh. So it's going to be negative J18. Then I will get negative J400 IA plus J100 here, IA minus IB. So if I simplify it, I will end up with okay, this is the first equation. The second equation is applying KVL in the second mesh. So we're getting negative 12 and J100 so let me just then I have 400 resistors, so it's going to be 400 IB plus 12 equals to 0. So if I simplify it, I will end up with negative 12 J100 IA plus 400 plus J100 IB. So now I have two equations, two unknowns. So let me write down. A1 is J300. B1 is minus J100. C1 is minus J18. A2 is minus J100. B2 is and C2 is minus 12. So D is going to be A1 B2 minus A2 B1, and if we do that, we'll get 40,000 minus 120,000. D1 is going to be C1 B2 minus C2 B1, and it's going to be 1800 minus J2400. Okay, D2 is going to be A1 C2 minus A2 C1, so it's going to be 1800 plus J 3600. So now I can find IA IB and IC, IA and IB. So IA is going to be D1 divided by D, and this is going to be 67.5 minus J75 milliampere. IB is going to be D2 divided by D, and it's going to be negative 22.5 plus J 22.5 milliampere. So V naught is going to be IA minus IB by applying KCL here, this current. I naught is going to be IA minus IB multiplied by the impedance, which is 100, J100. Okay, so this is V naught, and remember here we're asked to find the steady state expression for V naught of t, so we need to apply the inverse phasor transform here. So V naught of t okay, so you see here that we did not apply anything new. Everything we did in chapter 4, we applied it here. The only difference here is that we're dealing with complex numbers instead of real numbers. And you have to be familiar with this. So you need to solve problems in your textbook. And you'll notice that in your textbook, they're slightly using different techniques, especially when it comes to finding or manipulating the equations. I found it much simpler if we have a systematic way. And apparently the systematic way is actually by applying Kramer's rule. Any questions, Shabab? Adi?
Doctor, will be asked about the power.
Not really, because the power is a different issue. It's something that you're going to, something that you will be. I mean, if you have a question on this subject, you might be asked on the steady state power, but not in the complex domain. Okay. The reason for that is you will see inshallah in E213 is that you have complex power. So the power has real part and the imaginary part. So the real part is the dissipating power, and the imaginary part is the storing power. But it's the power calculation is actually left for chapter 10.
Okay, thank you.
Rahim?
Doctor, could you go back to the slide that we were having only one unknown? I think it was V1.
This one?
I think, yes.
Yes.
I tried to solve it in my calculator and it's not solving it. Maybe we should take the J up to the numerator first.
Yeah, you can multiply both sides by J20, for example. In this case, you'll have imaginary parts in the numerator. You don't have imaginary. I do know, like dealing with calculators. I haven't used calculator for almost 4 years, so I don't know how to. I don't know what type of calculator you have. But I know that calculators will allow you to actually multiply and divide complex numbers, but it will not allow you to multiply or divide to invert a matrix with a complex number. So you may try to do the following. Does your calculator allow you to mix between polar and Cartesian?
Yes.
Okay. So maybe in this case, because again here, you say it's not giving you 10 and the angle is 45, or it's not giving you a solution anymore.
It's when I click on solve, it's doing nothing. It doesn't continue as it should.
I think in order to solve a system of equations, you need at least 2 equations. So what is the second equation?
But here we have one unknown.
Okay, but I don't know about the situation. I don't know what type of calculator you have. So try to do it the following. Try to take V1 as a common factor. So you will get 1 over 20, 1 plus 1 over J10 minus 1 over J20. So this is the coefficient of V1. Then divide 2, the angle is 45, by this coefficient. Let's see if you can get V1.
Okay, I'll try it.
Okay, so you can find this problem is actually in your textbook. Any other question? Okay, just a reminder, tomorrow inshallah we'll have quiz 5, the last quiz. It's going to be in chapter 8. So please be prepared. طيب Aziz.
Doctor, if I want to check for the grade, the score of homework 3, who can I call?
You can request regrading for homework 3. There's an option for
what quiz 3?
What's that?
What about quiz 3? If I want to check it.
Quiz 3, yeah, you can check with me.
So, when is your office hour?
Today from 1 to 1:50.
Okay.
Any other questions, Shabab? Abdullah?
Just to make sure, are we allowed to use the formula sheet for tomorrow's quiz?
Yes. I'm probably gonna add it to the problem statement.
So we don't need to bring the paper ourselves.
No need for doing this. I'll probably add it to the quiz. So the quiz, instead of having like one single page, it will have 3 pages. 2 for the formula sheet.
Okay, thank you.
Okay. Okay, you don't have any questions, so see you inshallah tomorrow.